we're talking about design options for improving the cache performance. And here we have a summary in the table which can predict some cache performance improvement techniques. We have talked about way predictions, that means the for set associative. This does lower the hit time. For cache capacity, for example, if we have a small cache, that means our cache memory gonna be very, very fast, as we have learned when we talked about the memory hierarchy. The high-level memories, they are very fast, and as the size of the memory decreases, the speed increase. For larger line size, here we are talking about the line size. This can reduce the miss rate. It can reduce the miss rate. So when it comes to the cache associativity, for example, for one-way set associative, that means we have the direct map with speculation. Let's say with speculation, this is gonna lower the hit time. For fully associative, if you still remember, for fully associative, a cache from the break memory can be mapped into any cache location. So this can lower the hit time. We have also the fully associative, which can have a higher hit time. So here we have the right policy that we just learned. For the right policy, we have seen that we have two types of cache right policy, including the write through, which does update both cache memory and main memory at the same time. And we have the write back, which only updates the cache memory, and the main memory will be updated when the block from the cache memory is about to be replaced. So for the write through, this write through with write allocated means that it can lower the miss rate. For write policy without write allocated, it has a very important impact, a positive impact on lowering the time, the miss time. How long does it take the system to retrieve the data if it's not available into the cache memory? Now, this is the end of the lecture number 15. We did cover the cache memory, especially we talked about the logical cache memory organization. We talked about cache mapping techniques, direct map, fully associative, and set way associative. And we talked about the write policy, and we talked about design option for improving cache memory is performance. So I would like to know if there is any question related to the cache memory. Any question related to the cache memory? Seems there is no question, so we're gonna continue with the next lecture, which is lecture number 16. Lecture number 16. Lecture number 16, we're gonna continue with internal memory. But we do have to review the cache memory. Why? The cache memory also is one of the internal memory. But we did spend enough time on the cache memory as we had to discover how important it is, how does it work, what are the cache mapping techniques, How can we evaluate the cache memory is performance? How can we have some good design option for improving the cache memory is performance? Now, if someone asks you what are the internal memory computer system, what is the answer? This is depending on the location. Internal memory system in the computer system. What are they? What are they? Internal memory system in our computer system. I want you to name at least 3 internal memory system in our computer system. What are they? Huh? We do call them internal based on is the location. Internal, external. So what are the internal memory system? So if you still remember, the first one is the cache, the register. The register is one of the internal memory system. As you see, it is incorporated into our central processing unit. The next one is cache memory. That's why we needed to talk about the cache memory as well. Then we have the main memory. So these are the internal memory. That's why we needed to review the cache memory. We have registers here, which are integrated into the central processing unit. Then we have different levels of the cache memory. Then we have the main memory. Then we have the secondary storage memory. So we are talking about all these memory, excluding the secondary storage memory. All those memory, excluding this one, these not include into the internal memory. The secondary storage memory, the HDDs, they are called external memory based on the location. Now, cache design, if you still remember, it is designed to combine the access time of expensive high-speed memory and the large memory size of less expensive and the lower speeds. So we have the cache memory here, which is in between the central processing unit and the main memory. And the unit of transfer between the central processing unit and the cache memory is a weight. And the unit of transfer between the cache memory and the main memory is a block of data. Then this picture expands the previous one by including the different levels of the cache memory. As we have seen, we have level 1, level 2. Level 2 that seem to be bigger than level 1, but it is slower if you compare to the level 1 memory. And the level 3 is bigger but slower if you compare it to the level 2 memory. Then we talked about the cache mapping techniques because we know that the cache memory is smaller than the main memory. That means not all the blocks from the main memory can be loaded into the cache memory at the same time. We need to learn different cache mapping techniques, including the direct map. Each main memory block needs to be mapped into only one possible cache line. Here is the mapping expressions that can be used to find a cache line for a specific main memory location. Now we have a fully associative. We do not have to split the address into the tag and the index, only the tag, because we do not need to know the line number beforehand. So any address from the main memory, any block from the main memory can be loaded into any cache location, into any cache line. Then we have set away associative, anyway set associative. The address needs to be spent into tag and index because the index needs to be immediately addressed into the set, into the cache. Each set has multiple places. Each set has multiple lines for each index. Now, the first memory, internal memory after the cache memory that we needed to learn is the DDR, DRAM. That stands for double data rate DRAM, DRAM which is the direct random access memory. So main memory interface is a major bottleneck in high-performance computer system, in high-performance processors. So it is the most critical data pathway in the computer system. That means that the DRAM remains useful in the fundamental building block of the main memory, but the DRAM architecture stayed largely unchanged from the 1970s until now. Now, what are the limitations of the DRAM memory? We have limitations linked with internal chip architecture of the DRAM memory, and also we have some limitations linked with the interface to the processor is memory bus system. Now, one common performance solution is to add a static RAM between the central processing unit and the DRAM. But if you still remember, the static RAM is very expensive. Another possible solution is to increase the cache size, but this will reduce the performance of the computer system, because as the size of the memory increase, the speed will decrease. Since the size of the cache memory will be increased, that means the speed of the computer system will be decreased. That means it will take a lot of time for the system to retrieve the data, even though it is in the cache memory. Now, there are some recent improvements on the DRAM itself. Does include the synchronous DRAM and the DDR that we just talked before. DDR DRAM, double data rate dynamic random access memory. Now, we're gonna talk about the synchronous DRAM. The synchronous DRAM is now widely used in DRAM type memory. Like traditional DRAM, this memory is synchronous, is not asynchronous. That means that the data transfer is coordinated with an external clock signal. This is very important because it does run in synchronization with the processor or the memory bus system at a full speed. So because there is this clock which helps this memory system to be in synchronization with the processor or the memory bus at full speed, this is gonna have a significant impact. It's gonna have a positive impact on the memory system, overall on the computer system, because it does avoid wait state that has been seen in the traditional DRAM. So for SDRAM, that is the synchronous DRAM, is widely used in nowadays DRAM. And unlikely the traditional DRAM, the SDRAM is synchronous. That means the data transfer is coordinated with external clock signal. It helps the system to be in synchronization with the processor or the memory system, bus at full speed. This reduce the wait state that has been observed in traditional DLAM. Now, how does the traditional DLAM operation works? We have the CPU which sends the address as well as control signal to retrieve the data from the DLAM. Then the DLAM, we perform what we call internal operations. That means it has to select a row out of thousands of words. Then once the word is selected, there is the colon strobe that needs to activate a cell into the specific word. So this is a traditional way of the DLAM operation. Then the access time for the DLAM delays needed to force the central processing unit to wait because of this operation of selecting a word out of thousands of words. This will allow the central processing unit to be in waiting state. This has a negative impact on the computer's performance. So this needs to be solved by the synchronous DLAM by having the following operations when it comes to the read of the data. We have the central processing unit which sends the instructions as well as the address to the SLAM. And because the SDLAM is in the synchronization with external clock, what happens? The SLAM needs to use what we call latch, the request, and the data transfer will happen after a fixed number of clock cycles. So there is a fixed number of clock cycles to return the data to the central processing unit. This gonna avoid the CPU to be in long waiting time, and the CPU can perform other tasks while waiting for this delay. So this does improve overall computer system efficiency and concurrency. So normally the improvement here is based on the SLAM operation. If you can see here, the CPU has to send the instruction and the address, and the SDLAM latches this request, and the data transfer needed to be done after a fixed number of clock cycle. And since it is in synchronization with the central processing unit, the central processing unit can avoid this delay because it knows how many clock cycles it will take the SDLAM to return the data. Then the central processing unit can spend that time doing other tasks, which is in the opposite for the traditional DLAM, where the central processing unit needed to wait until the data is returned by the central processing, the DLAM. Now we have a simple example of a 250 megabyte SDLAM. We have internal logic of a typical of 250 megabyte SDLAM, and here you see that the SDLAM use a burst mode to improve the data transfer efficiency, and this burst mode eliminates what we call address setup time. That is the low or the colon pre-charge delay after the fast access. That means for the burst mode, we have this burst mode that works as follows. After fast data item is accessed, then we have remaining data in the sequence which is output rapidly. Now we have the command decoder and the clock generator. We have the mode register. Then we have the row address latch. This is very important. Then we have the row address buffer. Then we have the colon address latch then this is the bus counter. Once the first item of the data is read from the static lamp, the next one will be output rapidly because of the burst mode. Now we have the synchronous DRAM, which include multiple banks architecture, which enable what we call internal parallelism. This does improve the performance of the computer system by handling multiple operations simultaneously. So that means because we have the central processing unit which can get access to multiple banks of the memory system, that means we have the central processing unit to handle multiple operations at the same time, which can improve the computer performance. So this allows, again, customization of the static, the synchronous DRAM behavior, because the programmer can have to configure the system parameters. Now, the SDRAM include multiple bank architecture to allow the processor to perform multiple operations at the same time. Now, we have mode register control. Here we have the mode register control. Mode register control. We're going to talk about this mode register control in SDRAM memory. So for mode register control, we have a burst length. That is the number of data units that need to be transferred by burst. That means we have the latency between the read request and the data output. So what is the best performance condition for the synchronous DRAM? It has a larger and sequential data transfer. So this is what we are looking for. We are looking for a large and very high-speed data transfer. Typical applications for synchronous DRAM include word processing, speed sheets, or multimedia processing. So there are many other applications of this synchronous DRAM. Then we have the SDRAM pin assignment. We have the pin A0 to the pin A13, which is used for address input. Then since we know that for the SDRAM, it does include multiple banks architecture, we need the bank address lines. We have bank address line 0 and the bank address line 1 to set up the multi-architecture system bank. We have the clock enable for the SDRAM memory, and we have the low address strobe and the current address strobe as well. The current address strobe and the low address strobe, we talk this for other type of memory. This allow the low address strobe allows the system to select a word out of 1,000 of words, and once a word is selected, the system may select a cell within a specific weight. Then we have data input and output, as well as the data mask. Here we have the SDRAM read timing. This is the read timing with a burst length of 4. This is a simple example of the SDRAM reading timing, but only for a burst of length 4, and the colon slope latency is 2. Now we have a timing diagrams which show how the signal levels are over the time. We have binary conventions. We have 1. That means the 1 means the high signal level. Now 0 means low signal. 1 means high signal level, and 0 means low signal level. Then we have signal transition. there is signal transition from 0 to 1, that is the leading edge. From 0 to 1, here we have from 0 to 1, that is the leading edge. Then from 1 to 0, that is the trailing edge. 1 to 0, 1 to 0, that is the trailing edge. And we have transition that takes smaller. That is no instant time that needs to be taken for these transitions. These transitions have to take less time. Now, when it comes to signal grouping, signal categories, we have to represent multiple bits. They say we have 8 lines for 1 byte. For signal grouping, we also need to have a focus on the presence of signal, not exact value. We have here to talk about is this have a presence of a signal or not? That is what is very important, not only focus on exact value. We need to focus on the presence of the signal, not exact value. Then we have the lead command, lead for the A, and we can have non-operational signal for or 0 leading, and you can see that we have the data A0 which is out now. Then we can have the next data which can be out in less time. Now we have this example which only depict the timing operation for the SDLAM with a path length of 4 and colon address strobe latency which is 2. Then we can have the bus read condition. We have the colon address strobe which is low, and we have the white enable which is high for the low address strobe. This can help the system to select a word out of million of words. Then after the word is selected, a specific cell can be selected within the word. Then there is address input that needed to be specified, starting from the colon address. That means the system needed to select input, needed to specify input by starting the colon address. Then we can have the mode register to define the bus type. Is this sequential or it is interleaved? Then we have the bus length. The bus length is 1, 2, 3, 1, 2, 4, or 8, or a full page. So this is just a simple example of the synchronous DLAM lead timing. We have a bus length of 4 and a colon address strobe latency of 2. All right, then we have the DDR SDLAM. The DDR memory stands for double data rate, and it indicates that a memory technology that transfer data on both rising and falling edge of the clock signal. So it's effective doubling the data rate. So the SDLAM improves on asynchronous random access memory, but it does still have some limitation to achieve higher input-output data rate. So that's why need some advancement in developing the next memory system that we're gonna talk, which is the DDR DLAM, which was developed by this GDIC Solid State Technology Association to address the limitation faced by the synchronous DLAM, which was widely used in the computer system. Now we have this DDR SDLAM, which is widely used in computer system and in servers. How does this increase the data rate, especially for input-output data rate? It transfer data on both rising and falling clock edge. That means it has to double the throughput. It uses high bus clock speed. Now, it has to use this high bus clock speed to enable the transfer on both rising and falling clock edges. And this we have to double the throughput of the computer system. And also it employs the buffer, the prefetch into the data flow. So what does this mean? Prefetch buffer concept. Now we know that small cache memory have high speed, so we need a small cache memory on the synchronous DRAM chip, which can help to fetch multiple bit per access. Then it can bridge slower DRAM call and faster input-output interface via what we call parallel access and serialization, which we call also multiplexer. This will enable what we call continuous high-speed data transfer. Then we have the DDR generation. We're going to talk about these probably next class. I would like to know if there is any question up to now. Questions up to this slide about today's class or previous classes, especially lectures related to cache memory. Question? We're going to talk about the DDR generation next class. Since there is no question, we're going to have a very short in-class quiz. On cache memory, as I said before, last class, we're going to have a short in-class quiz. 10-minute quiz. introduction. That's it for today's class. Make sure you do finish your lab assignment number 3 by today before it closes. And tomorrow or day after tomorrow, I'm gonna upload lab assignment number 4 as well as homework number 4. All right, I'll see you next time.